In this section, we'll take a look at the Layer 2 Bridging Concepts objective of the JNCIS Service Provider exam. We'll examine basic bridging theory, virtual switches, and provider backbone bridging. For more detailed coverage of this objective and more, please check out the Juniper Service Provider Switching course.
In this video, we're going to take a look at bridging. So with bridging, our goal is to segment collision domains within a layer 2 segment. And we achieve this goal by building, maintaining, and using a forwarding table. An example of which we have on the board here. A forwarding table, a MAC address table, is an association between MAC address and interface that's built and used on a learning bridge or a switch. And the functions that a learning bridge or a switch uses in conjunction with a forwarding table are outlined on the board here. The first is learning. So in our example here, say host A is sending a frame to host C. The source MAC address is A, the destination MAC address is C. The frame arrives on the switch on interface 1. The switch then builds a forwarding entry based on the source MAC address and the incoming interface. So we have an association between MAC address A and interface 1. And this is one of the main ways in which the forwarding table, the MAC address table, is built. Next, we need to send traffic utilizing this forwarding table. This is where the forwarding function comes in. So this frame is now on the switch, destined for host C. We look up in the forwarding table host C's MAC address. We see that the port is 2. So we send this frame out of port 2, out of interface 2, on the way to host C. That's the forwarding functionality of a learning bridge. But what if we don't know the location of a particular host? In this example here, host B is not yet present in the forwarding table of our switch. And say host C is sending traffic to host B's MAC address. This frame arrives on the switch. What the switch then does is it uses the flooding functionality. What this means is that this frame, destined for MAC address B, is sent out of all ports on this switch, apart from the one that initially received that frame. And this way, this frame arrives at host B. In all likelihood, host B is going to reply to this frame. So he's going to send a frame with his source MAC address of B and the destination MAC address of C. And this frame then arrives on the switch. This allows the switch to then add MAC address B bound to interface 1 to his forwarding table. And that way we are completing the forwarding table. So this was an example of unknown unicast flooding that we use when we don't know where that unicast MAC address exists. Flooding can also be used to deal with broadcast and multicast traffic. The next feature of a learning bridge is filtering. Say host A and host B are interconnected via a dumb hub, and that hub is then interconnected to our intelligent switch. Host A sends traffic to host B, and this hub is flooding that traffic out of all ports. So a frame from source A, destination B, arrives on our intelligent switch. Our switch does a lookup in the forwarding table. He filters this frame to prevent any unnecessary flooding further down in the network. And then finally, we have the aging feature of a learning bridge. So this is that the entries in the forwarding table are periodically aged out. This allows us to keep the state that a switch is maintaining current. And it means that we're not forwarding traffic to destinations that no longer exist. And this is a quick overview of some of the basic features of a learning bridge. In this video, we're going to take a quick look at virtual switches. So virtual switches are much like layer 3 routing instances. In fact, you configure them in exactly the same way. You're configuring them under the routing instance stanza in Junos configuration. It's just you're specifying that they are the type virtual switch rather than, say, a virtual router or a VRF. And much like layer 3 routing instances, we're just providing logical separation between different logical domains. It's just that we're dealing with layer 2 here rather than layer 3. With virtual switches, what you're getting is you're getting separate layer 2 namespace. So you have the set of VLANs that you want to use allocated per virtual switch, and you can use the same VLANs again and again per virtual switch, much like you can use the same IP addressing in separate virtual routers. And much like virtual routers as well, you have separate forwarding tables. With virtual routers, you've got separate routing tables per virtual router. With virtual switches, you have separate MAC tables per virtual switch. And to illustrate these concepts further, I've drawn up the internals of an example Juniper router on the right-hand side of the board. And we've got our various different tables that are interconnected. And let's walk through how they all interplay together. So we have our parent IPv4 routing table, inet.0, at the top here. We've got the default switch MAC tables down at the bottom. So this is when you have just bridge domains configured outside of routing instances. So just at the parent configuration level, you are configuring bridge domains on your MX device. And we also have an example of a virtual switch configured here, VS1. And this is a virtual switch that's been configured under routing instances. So you can see that the MAC tables are separate for our default switch instance and our virtual switch instance. And if you were to configure additional virtual switch instances, they would then also have separate MAC tables. And you can be associating VLAN 20 here, VLAN 20 here, VLAN 20 on another virtual switch, and that VLAN 20 in each of these tables is completely separate. There's no flooding link between those VLAN 20s. They're all completely segregated between the virtual switches themselves and the virtual switches and the default switch instance. If you wanted to interconnect either VLANs in the default switch or VLANs in virtual switches with the inet.0 routing table, i.e. you want to provide a layer 3 gateway for hosts that are connected to your layer 2 domains, then to do this you use IRB interfaces. You configure a routing interface under your bridge domain, either in your default switch or in your virtual switch, and this routing interface is going to be an IRB interface. And the IRB interface, whether it's for your main default switch instance or any virtual switch instance, by default gets placed in the main master routing table, the inet.0 routing table. So we have our separate MAC tables here with our switching instances. And you would of course associate interfaces with these tables. If you're doing this for a virtual switch, you would configure it under the routing instance exactly like you would a layer 3 routing instance. You specify interface and the interface name under the routing instance name, and that associates those interfaces with those tables. If you wanted to interconnect virtual switch instances, you can do that with an external loop. So you'd have a physical piece of copper or fiber connecting two ports on your device. One port would live in one virtual switch, another port would live in another virtual switch. And that way you can interconnect your different separate virtual switch instances. And this is a quick overview of virtual switches. In this video, we're going to take a look at provider bridging. This is covered by the IEEE standard of 802.1ad and is also sometimes referred to as Q-in-Q encapsulation. So what problem are we trying to solve here? Well, imagine you are a service provider who's running a multi-tenant network providing layer 2 services to multiple customers. The 4094 VLANs that you get with 802.1q encapsulation aren't going to scale to very many customers if those customers require multiple VLANs. So we need a different technique to be able to have a much larger layer 2 namespace to play around with so that we can support many customers, each requiring many VLANs when we're operating a service provider network. And this is what provider bridging allows us to do. We're solving this problem by having stacked VLAN tags in the Ethernet header, much like we could have stacked MPLS labels in an MPLS environment. I've illustrated this on the top portion of the board here. We have a typical Ethernet frame. We've got our IP packet, and it's encapsulated in an Ethernet header where we've got our destination MAC address and our source MAC address. What we're doing with provider bridging is we're inserting two VLAN tags here. We've got a inner VLAN tag, which is sometimes called the C tag, the customer tag, and this has a tag protocol ID the same as an 802.1q VLAN of 8100. The key here is that we're then adding an additional outer VLAN tag, an S tag, a service tag, and this has a different tag protocol ID value of 88A8. And what we're doing here is the C tag, the customer tag, these are the customer specific VLANs, the VLANs that the customer are going to use on their own site. And then the S tag is the tag that's relevant to the service provider, and this tag is what identifies each of the individual customers that this particular Ethernet service provider is servicing. So this is the frame format. What do the different elements of the network architecture of a provider bridging network look like? This is what we have outlined on the bottom portion of the board. And the elements are fairly similar in role to what you'd expect in an MPLS service provider environment. We have our customer devices. In this case, we have customer switches on the far edge, and then we have our service provider portion of the network in the middle. We have our provider edge bridges. So these are the devices that are interconnecting to the customer switches. And what they're doing is, on receipt of a frame from a customer, they're pushing an S tag onto the frame. This frame then traverses through the service provider network, and on the egress provider edge bridge, we're popping that S tag off and passing a standard 802.1q encapsulated packet to the customer. And then on the intermediary portion of the provider network, we have provider bridges, and they're performing standard layer 2 switching on the S tag, the outermost tag of the frame up here. If this provider was interconnected with another provider, or there were two portions of a provider's network interconnected, provider bridges can be swapping the S tag to a value that's locally relevant to the network that he's passing that Ethernet traffic onto. And so, as you can see, with this addition of a outer S tag to a Ethernet frame, we can support a very large number of customers and those customers can have a very large number of VLANs in a service provider Ethernet environment. And this is a quick overview of provider bridging.